Okay, so essentially what I want to do here is show you guys a little bit about how to make the controller. So here I have the microprocessor. There's nothing really surprising about this, right? So here we have a clock, reset, read, write, address, and data. Now, we have to remember where these are coming from and going to. So data is that in out that we spent so much effort and time thinking about, right? So that's the kind of internal data bus. Um, Address here, oh shoot, sorry, clicking on stuff. You can see is just getting address is equal to PC when fetched, otherwise mar, right? So that's the address that's coming from our PC. So that's all that is. And that there is an output that's going to go to the memory. Read and write are, again, outputs that are going to the memory. So that's how this is designed. I won't go into the ALU. Hopefully you guys have a working kind of ALU microprocessor. What I want to focus on here is the really the final project, right? Where we're kind of building up the brains for this thing so that we can just pass it a command from memory and have it execute as it's supposed to. So here, let's start off at the very top for this test bench. I'm using numeric standard as always. It's a test bench. So here's that declaration for the microprocessor that I walked through. Here I'm just creating some signals. We know we have to make them. You go ahead and make your test bench signals. Here I'm declaring the constants that are the operations, right? So halt is 0, jump is 1, and so on and so forth. So that these are tied into my microcontroller so that it knows that when it gets a halt, for example, it knows what to do. Okay, so the next thing is that you want to have this memory, and this is literally just copy and paste from the lab. There's nothing secret or special here, and all this is saying is that it's a memory is what they're calling it, but really all it is a 8, 7 down to 0 by 256 block of data. So each of these, OP-LDI and X9E, etc., each of these are just 8 bits of data. The X apostrophe, remember, is hexadecimal. So we have a command of load immediate and then load 9E as your immediate. Okay. So this is row 1, row 2, row 3, row 4, and so on. Everything else is just filled with ones, FF, where we can also use these to store data, like with save to memory commands, right? So, shoot, I keep dragging things around. So hopefully this makes sense to you. If it doesn't, you should really reach out to me and we can kind of go over it again. Here, this is what we call instantiation. This is where we're making the instance of the micro, where it has a clock, reset, read, write, address, data, right? This is making a clock. This was just copy and pasted code from elsewhere. This is not how I create clocks, but it's a way to create a clock, totally fine. This is a simple little process. You can copy and paste this just by pausing the video if you want to steal it. That just resets once, waits for a clock, and then sets re0, and then waits forever. So it just creates one reset at the beginning. Nothing fancy. Lastly, this is, again, just copied and pasted from the lab. What this is doing is accessing the memory. So what it's saying is, if you write, so if write is 1, then you take the RAM at address and put data into it, right? So if write data into RAM at this address. This conversion here is just converting address, which if you go look up, where is that? Is a standard logic vector. And here we want it to be an integer. So we're just doing that conversion inside. We're converting address to an integer and accessing RAM at that integer and saving data there. That's how we handle the write. This line, which again is available in the lab, is how we access read. So when read is equal to 1, we get RAM at address, otherwise Z, right? That's the same in-out kind of style that we talked about in project 2. Okay, so that's the test bench. And that's all it's stuck together. And all it's going to happen ideally is your process controller is going to set through 0, 1, 2, 3, 4, 5, right? These memory addresses, and then your microprocessor is going to handle the appropriate signals and generate like the read and write commands, um, load mar, load PC, all of those things that you need in order this work. So this is really replacing that kind of brute force method that we saw in Project 2's test bench. Okay, so let's go look at a little bit of how the microprocessor is going to work, um, in terms of the brain of the thing, right? So we've talked about state machines, and so you may guess that if you haven't started this, you're going to be very confused. So hopefully, you've at least started the project. Um, you're going to want different states to handle this control. So this is just one way of doing this. I am in lab. If you were in lab today, you would have seen me discuss a different way of doing this. Either one should work, but I wanted to talk about this one because I think this might make more sense on reflection for some for a lot of people. I think this will make more sense. Okay, so this one is going to have a couple different things, and I don't want you to just like start copying down my code because I don't think that's necessary if you have everything else. So I'm just going to highlight some of the most important parts. So let's scroll through and come into, so that's the state machine. So this process here is just taking every time that you get a rising edge of clock, it will take whatever is in next, NXT, and put it into current. So next state, current state. So we need to make sure we set up whatever next state is. All right. So this is one way of doing things that is interesting that you may find useful. So here, I'm setting the default values for all of the signals. So by default, fetch is true. Increment PC is true, and so on and so forth. Then I'm going to case on whatever my current state is. My default state is going to be, if you look at this next state, fetch. If I don't tell it to do something else, it will default to going back to fetch, where fetch is going to get the data and based on the command, go to a specific state. So this is when the command, when data is LDI, then next state is load immediate. State, load immediate. That's what that nomenclature, naming convention is. There we go. So let's go look at load SDI. It says, well, when I'm trying to load immediate, I send the opcode load to my ALU, right? So another command that I could do here is load from memory. Now, if you look, load from memory requires a little bit more thinking. It requires more than one clock cycle, really. So let's go look, load immediate. So let's say we started fetch because that's our default. We get the command load from memory. So our next state on the next clock cycle, we go to load memory 1. In load memory 1, we set load mar is equal to true because we're going to the mar, we're accessing the memory. Then the next state is this load memory 2 because we need more than one clock state. So step 1, set load mar is equal to true. Step 2, come to LDM2. Fetch becomes fault. We're no longer fetching, right? That's the PC controller that we've built. We're not incrementing the PC because we're fetching from the mar. And our opcode is load the ALU. Now you'll notice here, there is no NXT. There's no next state. Why is that okay? Because it defaults here. If this doesn't get overwritten, it defaults back to fetch, and the fetch is let's go get the next thing, right? And you'll notice when we fetch, also the default is increment PC. Step through the next one, let's get it. All right. So I want to, the rest of these, I'm not going to scroll through all of them because I don't want to give you all of the answers, but that should show you load immediate and load from memory. And that's the general way of this functioning with this default kind of fetch state in there. I did scroll through all of it. I just want to make sure I didn't forget something. So I don't want to make this too easy on you, but I want to make it a little bit easier because I know finals are coming and everybody's stressed with, well, life. So let's go ahead and look at the waveform so you at least know what we're kind of looking for. So here, this is really important. So anyone that doesn't know, your default situation is for it to display only top level signals. So let's run this simulation. I'll start from the beginning. Let's run a simulation. Sorry, hopefully I didn't introduce any errors that's going to cause issues as I drag things around. Okay, perfect. So let's start by, I don't know if you guys can see that. Okay, so let's start just by looking at this guy, right? So I have all of these opcodes. They're in here because they're signals, but they're constants. So I don't really care about those. So I'm going to highlight them all and delete them just so they don't clutter up my test bench. Now, part of the issue is here, I can't really see what's happening inside of my microcontroller, and that's a problem. So what we do is over here on the left, we click on scope. We click on our microcontroller. So scope, and then we click on this objects. And now this is all of what we call the internal signals. I've mentioned this before, but some people have missed it. And this is really kind of an important idea because now I can come in here and literally take all of my internal signals, fetch, increment, load, write, that's the carry, the current, and next states. And I can drag them all here. Let me make sure there's nothing else that I want. I think that's all fine. So then I'm going to minimize those, just get out of the way. And you'll notice that there's nothing here yet. I just have to hit refresh. It'll rerun the simulation. And once it's done that, we can look at the internal signals. And that's just going to make our life a little bit easier to see what's happening. So let's go take a look. We know from our lab, if we go back and look at the memory, the first thing that's going to happen, it's going to load immediate and add immediate. Okay, so that's what we're looking for, load, add. So this is our waveform, a little bit of clutter. So let's zoom in. So starting from the beginning, we have fetch, right? That's our current state. That's our default state. You'll notice at the moment the reset is 1. So nothing interesting happens till here when reset goes to 0. After that, we can start looking what happens at these clock edges. So something else that you can do is if I click on this trace, the clock, I can use my arrow keys right and left, and it will just jump to transitions. So let's look at this first rising edge of clock. So we are at fetch right here. Data, you see, is this 10 and then this 9E. And what's going to happen is we're going to load immediate and assert all the necessary signals. On the next clock cycle, we're back to fetch, right? Because that's our default state. After load, I need to go get the next command. After fetch, next clock cycle, we have add, right? Load this, 9E, add AA. Okay, let's go back and look. So we loaded 9E. And here, we can add AA. And then so on and so forth. After the add immediate, we've got this, let me scroll over a little bit. After the add immediate, we then go back to fetch. And then this STM, well, let's go look at that. Next operation is STM. Okay, so you can tell from this waveform, the STM takes one state here to do some setup, and then a second state to finish that execution, and then we're back to fetch, back to getting our command. So that's kind of the process that we can go through. Now, what I talked about in lab, the other way of doing this, so this is building the default state setting the default state to fetch. And we always go back to fetch, grab stuff, and go on. When I talked about it in the lab, what I was doing is inside of this state machine, instead of having the default state as fetch, I didn't even make the fetch state. I just kind of was building fetch into all the other states. So once you finished like load 1, load 2, then it would have an if statement essentially that would go and fetch the next and decide where to jump to, because you know once you're done with this next command, the next thing you have to do is fetch. I think on reflection, this way is probably will make more sense for you guys, and will probably ultimately actually save a couple lines of code to make it debug. So don't be too afraid to still just straight up hijack, if you want, to be honest, to simplify your lives, this section of code. I think this will make your lives a little bit easier and hopefully keep you guys a little bit happier for the holiday season, because I do want you to all to succeed in this. I know it's been a really hard semester. So I think I'm going to sign off there. I showed you the internal signals. That's really important for debug. Hopefully the state machine thing works. If any of you have further questions, make sure to reach out for me during office hours. So I'll have office hours Tuesday, Thursday, and Friday. They'll be extended beyond what I normally do, just so I can help you guys finish. Don't be afraid of reaching out. I know I can seem cranky sometimes when I'm helping. I really am not a cranky person. I'm happy to be helping with, even if I come off otherwise sometimes. So really, guys, best of luck. I hope this helps, and reach out if you need help.